Hello, hello, everyone. Good evening, good day, and welcome to another episode or second episode of Chemistry with Jappy. Okay, so please don't get guys. Please don't get upset. We're still focusing on differential equation. It's just been a hectic day, and there seems to be people sending activities of chemistry to us. There's something. So we're gonna answer this, and we're gonna answer this. It seems to be like some form of test again. Alright, we're gonna answer this, and this time I'm gonna take my time. Okay, I'm gonna take my time answering this because apparently we got our first commenter on our video. So someone got a little confused on our last episode or our last video about chemistry, and it kind of dawned on me, or I just kind of noticed that I was focusing on solving or answering the question very fast rather than teaching it, or like imparting what I know. Right? Not that what I know is the correct answer, but it's just what I know. Right? Okay, let's start. Uh, I think this is the same question. Wait, is this the same question? Uh, Although it's a problem-solving type. Where's my mouse? After, wait. I, okay, are we here? Wait. Wait, what? Chotomate. Nice. Okay, so we're here. Okay, so Grian, a general engineering student, is aiming for a major in chemical engineering. He told you a story about his experience in iron and corrosion and how to prevent it. Which branch of chemistry would you recommend closest to his problem? Corrosion is a type of oxidation, right? So when we say iron getting corroded, so the iron solid becomes iron oxide. Okay, so that's the chemical formula for rust. Okay, so it's not photochemistry. Well, certainly it's chemical engineering. Combustion is about oxygen to carbon dioxide or fuel to carbon dioxide, and iron is not surely fuel. So the answer, I think, is electrochemistry, because electrochemistry focuses on oxidation and reduction. Okay, especially metals. In redox reaction, you notice that the silver nitrate reactant produces a silver shiny precipitate. With the given data, what happened to the silver in the silver nitrate? The silver nitrate reactant produces become silvery shiny precipitate. Well, it could turn into silver. Silver is solid, right? Silver is silvery shiny. I don't know about nitrate. It could also turn into salt, but with the given information, silver is the only one there that is silvery and shiny, right? So certainly not frozen. No temperature is being talked about. Condense, yeah, no. Condense is vapor, about vapor. Reduction or oxidation? Well, in here, Ag is Ag plus, while if it becomes solid, it becomes neutral. So the answer will be positive. It becomes zero. Reduction. Okay, it's reduction. Okay, the silver became neutral. If it's Ag negative, it becomes 0. That's oxidation. Okay, ether reduction is adding electron or positive going lower, while positive 2 going lower, positive 1 0, right? Or oxidation is gaining an oxidation state. Ether made you to make a ether requires you to make a sword. Grammar wrong. From any of the given metal, which is the most applicable if the sword is to be used for display on an open area for a long time. Okay? Whew. Well, open area, meaning there's air. Okay, these two, okay, I'm sorry. Okay, so these two can rust, you see the green thing in copper and doorknobs. Yeah, copper is before is used in doorknobs. So if you see some green things in doorknobs, or like maybe medals, okay, that's copper rusting. Iron rust, So open area for a long time. Chromium. Okay, chromium is non-unrustable, or it cannot be corroded, right? Chromium cannot be corroded. So chromium could be used, could be used. Among the three, chromium could be used for, for a long time. If it's not chromium, copper could be, but copper could rust too. Plus, copper has a better shine than iron. Although iron is used for sword, but not for, iron could be used for sword, but not for display on an open area. That's why we have, like, you have a sheet for sword. Shit. Yeah. No, I'm sorry, YouTube, don't ban me, okay? I'm talking about this kind of shit, shit, there you go. Okay, in the reaction below, Lumine was asked to determine the following. Choose the letter of the correct answer. Okay, which is the reactant? Oh, this seems familiar. Okay, KBr is the reactant because it's on the left. On number 6, which is the product? Which is the product? KNO3 because it's on the right. Yeah, right. The arrow is an indicator of reactant going to product. A reaction going, going to the right. So wherever's the arrows going to, the opposite side it's going to is the reactant, while it's going to the product. Wagner was handling an unknown metal. He noticed the metal is very ductile and malleable, shiny and soft in a way, and non-corrosive. Which metal could it be? Pig iron is basically iron that is not processed. So, it's not shiny. It is ductile and malleable. But iron is corrosive. Okay? Cast iron is the same. It is still corrosive. Okay? Platinum is added to iron because it's platinum. It's very strong, very hard. Okay? And it's non-corrosive. Okay? I don't know about being very ductile or malleable. Right? But in terms of ductile and malleable, when we say ductile and malleable, it can be turned to wire, it can be turned to plates, it can be turned into tin foil, and aluminum is a very shiny material, and there's no such thing as aluminum corrosion. Okay, that's why we use them on food. Okay, aluminum sheet, aluminum foil. Okay, and the answer is aluminum. Okay, I hope you guys are learning, or are you guys like the slower version more. Okay, but I hope we have a, but with the slower version, I think we're gonna have like a longer video, and I hope you guys are like willing to watch the longer video. Feel free to comment what you'd like more. And if you guys are watching, I think you guys are watching for knowledge, right? So I think it's much better if I explain what I know. Grian, an aero engineering. Grian, you're chemical engineer and an aero engineer. What are you, a multitasker? Double major? Grian, you're such a smart guy. Okay, engineering student is asked to given multiple properties of, multiple properties. Odorless property of methane. Okay? Choose the letter of the closest answer that will describe the properties. No, oh my god, the letters. Odorless property of methane. Okay, the more methane it is, the more odorless it is. Okay, but odor is a physical property. Okay, because the more the material is, the stronger the odor, right? The stronger the concentration of odor in the air. Right? So I think it's an extrinsic physical property. Okay, extrinsic physical property. Okay, when you say physical, this changes with mass and substance. Okay. Sorry, when you say extrinsic. Okay, when you say extrinsic, this changes with mass and substance. When you say intrinsic, okay, it doesn't change with mass and substance. Okay, when you say intrinsic, okay, it doesn't change with mass and substance. When we say physical property, there's no reaction happening. It's just the property of the substance. When you say chemical property, the substance will change, or that property could change the substance reaction. When you say chemical property, okay. For example, is ignition point. When you say ignition point, it is the point where you can ignite, or by just having that temperature, the fuel will ignite, okay, without spark, without fire. Okay, by just having that heat, the material ignites. Okay, that is ignition point. And I think that is an intrinsic chemical property. Okay, because it doesn't change no matter how many material you have. Okay, it's the ignition point is still the same, and it will react. Okay, boiling point. Okay, so that is intrinsic. Okay, that is intrinsic. Okay, and I think that is intrinsic pre-physical property, because you will change, yes, in physically, you will become vapor. Okay, when you say boiling point, you will change physically. Your liquid, you will become gas. But chemically, you're still the same H2O. You're still the same chemical. Okay, boiling point. Okay. Okay, plus boiling point is where you change physical state. Which is physical property, right? Okay. Okay, gross calorific value. Okay. Gross calorific value. Gross calorific value is the amount of energy that you gain from combustion. Combustion is a reaction. That's a chemical property. And amount of energy you gain from a combustion per mass or per molecules of that fuel. So meaning it changes with mass, extrinsic property. Okay, extrinsic chemical property. Okay, food companies will always use this type of steel, known for its non-corrosiveness and formability. What do you use this type of steel? So chromium brass is not a type of steel. Cast iron is corrosive. can corrode. Chromium and brass are, sorry, chromium is a type of metal that you add to iron, okay? And also an element, right? Brass is a type of copper alloy. Okay, I don't know if there's a, I know brass is a type of copper alloy. Stainless steel is a type of iron, okay? And that doesn't corrode. Okay, and food companies use stainless steel equipment. Okay, the following cases was given to Eater. He was asked to choose the correct choice to which entropy is gained. Sodium chloride crystallized at the bottom of the kettle. Water and calamansi extract being mixed together. Evaporation of water to vapor. None of the above. So entropy is the chaoticness or the how random the particles is or the molecules is. Okay? And when we say chaoticness, it means they're very moving. Okay? And water and calamansi is just liquid to liquid. Okay? Yes, you're mixing them, but okay, there could be like a little entropy gain. Sodium chloride crystallized at the bottom of the kettle. If your material goes from liquid particles which very loose becomes solid, which is very compact, entropy is lost. Okay, so liquid, liquid, solid, evaporation of water to vapor from liquid material who's like has a freedom of only the container becomes vapor who's very loose and very active in the air. So that is the answer. Entropy is gain. Okay, these type of materials have almost no band gap and overlapping materials. So band gap is a type of property or a type of, well, I guess it's a property because it's basically the overlapping of the molecules, right? The overlapping of the molecules of the metals in a solid structure or molecule structure. Okay, so if there is no band gap, meaning overlapping materials, you're talking about a metal property which is conductors. Okay, right? So because the flow of electron can flow easily. Okay, if there's a gap between those molecules, okay, the electrons cannot flow easily. It's insulators, while semiconductors have like alternating band gaps or random band gaps. Okay, okay, you're near the ocean, out of water. You tried to boil water and found that white precipitate forms. Ooh, and what metals probably made up that white precipitate? Calcium. I know it's calcium and magnesium. Okay, I know it's calcium and magnesium. It's not potassium and sulfur purpose, but blah, blah, blah. Okay, so it's gonna be B. Okay, the only metals in abundant in the ocean is calcium and magnesium. Okay, it could be sodium too. You know, it's very salty, but calcium and magnesium forms the limestone, forms the chalk. No, the limestone and the slate lime under the ocean. They form the rocks under the ocean. Klee is so happy to finally get the chance to play with her fireworks. She wanted to make a fire using solid fuels. Which properties of solid fuels is true? Solid fuels combustion is very hard to control. Solid fuels generally leaves little to no materials after combustion. Solid fuels cost too much. Solid fuels is very cheap. Okay, you can get charcoal for free. You know, they're very cheap compared to the liquid and gas. Solid fuels generally leaves little to no materials after. No, hell no. I'm sorry YouTube. I'm sorry. No. Charcoal leaves ashes, so it's a big no. Solid fuels combustion is very hard to control. Yes, dude, I'm having a hard time cooking pork chop in like charcoal. You know, they always get burnt because the fire is very inconsistent. Sometimes the fire goes where the wind is. Sometimes the fire just like blah 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 blah. In 2009 all-time favorite block game, Minecraft. This fuel is known to be the most efficient fuel, notorious for its capability to melt its container at the same time. Oh, I know that. Lava. So in Minecraft, lava can be, you can gather lava by a bucket, steel bucket, iron bucket. But iron can be melted by lava, but when you use the iron bucket on the lava, you can get the lava. But it melts the iron bucket when you're not using it. You know. And you can throw the lava on the lava, which in turn melts the lava. Okay, anyways. Lava. I love you, lot. Okay, I'm gonna shut up. I'm gonna shut up. I hope you guys are like enjoying the longer video. How many minutes do we have? 20 minutes for that. I think that's very, very cool. Very cool, yeah. A cylindrical barrel of alcohol is, oh, this seems familiar, okay? So you have a cylinder barrel of 2:1 height to diameter length ratio. Okay. If a certain rum brand has a 0.6 pound mass gallon, how much alcohol in grams do we have? We have 500 liters. Okay. So 0.6 pound mass, we need grams, right? Okay. Okay. So gallon can be converted to 1 gallon is 3.785 liters. Okay. Right? 3.785 liters. Okay. Then I know that pound is always bigger in number. So 2.205 pound is 1 kilogram. Then 1,000 gram is 1 kilogram. Then multiply 500 liters. To cancel the liters, okay. Okay, what do we have? Poof, we got copra. Divided by 3.785. Oh my god, why did I? Okay, 0.6 divided by 3.785. Can I divide it? Divided by 2.205 times 1,000 times 500. We got 35,945. Oh, let's double check. 0.65 divided by 3.785 divided by 2.205 times 1,000 times 1. 35,945.6861. 35,945.6861 grams of alcohol. Okay, that's pretty good. That's 500 liters. And that's like 35 kilogram. Oh, that's good. That's pretty cool. Cause to be fair, okay, to be fair, wait. To be fair, water is 1 kilogram, 1 liter. So if 500 liters, that's 500 kilogram. And we have 0.6 pound mass per gallon, which is, I think it's a lot smaller. Okay. Consider a barrel's base diameter is 2 feet. How many barrels will 3,000 liter will fill? Okay. So 3,000 liter will fill. Right? 3,000 liter is 2 feet. Okay, so we don't need mass anymore, right? So let's just convert 1,000 liter into 1 meter cube. Okay, that's the volume of the 1 barrel. Okay, or that's the volume of the, that's the volume of the 3,000 liter. Right? Let's compute how many volume will 1 barrel get, right? So the question says barrel's base diameter is 2 feet. Sorry for the dogs. And it's like 2:1 height to diameter ratio. So if your diameter is 2 feet, 2:1 height to diameter ratio, so your height is 4 feet, right? So meaning your volume is pi d squared over 4h. Okay, or that's pi 2 square over 4 cancel 4 pi. Okay, that's our volume per barrel. And the question, volume per barrel, no? Per barrel, right? So the question is 3 meter cube divided by 4 pi feet cube. How many numbers of barrel is that? Right? Let's just convert. Okay? Let's just convert meter cube to feet cube. Okay? 0.3048 meter is 1 feet. Right? Then cube that. So it becomes cube. How many barrels do we have? Okay. 3 divided by 0.3048 divided by 4 divided by 5. 0.7832. Okay, 0.78. Barrel, units or barrel. Okay, so it's not even like 1 barrel. Okay, it's not even 1 barrel. 3,000 liters. 3 meter cube. Okay. To be fair, 3 meter cube 1,000 liter is 3 meter cube. That's pretty big. But we have like 3,000 liter. And that's 3 meter cube. And base diameter is 2 feet. Oh, wait, did we cube? I think we didn't cube. Oh, okay. Double check. Okay, because yeah, we should always double check our answer. Physically, I'm having doubts because that's 3,000 liters. Right? That's 3,000 liters. How many is that? And feet is just my feet length, 1 ruler, right? So 2 feet barrel, that's pretty small. So that should be cube. There we go. I think that's a more believable answer. Okay, that's a more that's a more believable answer. I will believe that more. Okay. Okay, that's one of the fun things in science, right? The answer should be believable or probably, correct. 3 divided by 4 pi. I think we did 2 square 4 pi r squared h. And that's cylinder, okay? So 8.4308. Number of barrel 8.4308. I would believe that. Yeah, I would believe that. 8 barrels. Okay? 8 barrels. I would believe that. 1 feet is basically 1 ruler, right? Yeah, I would believe that. 8 barrels. Yeah, pretty good. Okay, 0.3048 meter. Okay, 1 feet is 0.3048 meter. Okay. Or 1 meter. Okay. Sorry. Or see, 2.54 inch is 1 centimeter. Oh, wrong. That's wrong. Wait. 2.54 centimeter is 1 inch, okay? And 30.48 centimeter is 1 feet. Okay, okay. I believe them. That's correct. I don't think we're wrong now. Okay, that's the final answer. Double check, it doesn't hurt to double check your answer. It doesn't hurt to like reconceptualize what you think. 3,000 liters, I would believe that. 8 barrels, 9 barrels, I would believe that. Okay, Hess law. Okay. So Hess law is basically getting your equation or making your equation from smaller equation. Balance the equation of the combustion of ethane below. C2H6 plus O2 going to H2O plus CO2. So there's 2 carbon. Okay. There's 2 carbon. There's 3 oxygen. There's 6 hydrogen. So we're gonna make, hydrogen 3. Okay. How about let's do this? Okay. There's 2 carbon here. So let's make 2C. Okay. So there's like 6 hydrogen here. So let's make like 3H2. Then there's like 3 oxygen here. Okay. Then there's like 4 oxygen here from 2 times 2 O2, right? So that's 7. Okay, so this will become 7 divided by 2. Okay, 7 divided by 2 oxygen. Or we can make like, okay, you can make like 2 C2H6 plus 7 O2 going 3 6 H2O plus 4 CO2. Okay, this is also good. This is also good. Some in combustion in fuels, this is also correct. In stoichiometry, we don't take half molecules because you cannot take half of a molecule, right? You cannot take a half of a molecule. Okay, now I'm gonna use this. Now that we have this equation, let's make our equation. Since we have C2H6, we're gonna get C2H6. There we go. This one at the bottom, right? C2H6, C2H6. Oh my god, what's happening? H2O. Okay. 6. Oh, sorry. 6H2O 4CO2. Okay. Okay. So next C2H6 going to C2 and H2, 3H2, right? Or 3C, no, 2C, no, 2C. There we go. 2C, 3H2. That's our C2H6. We need to make 2 of these, right? 2. So because we like converted it to the opposite side, because on our table it's C and H2 going, carbon and hydrogen going to C2H6. On what we wrote, it's C2H6 going to carbon and hydrogen. We're gonna put a negative on the heat here. Negative 85 kilojoule per mole times 2, because we multiply the equation times 2. Okay, next, I think this should be like gas. Everything is gas. So we're gonna use this H2O gas. Okay, H2O. H2O2. Okay. H2 plus 1/2 O2 going to H2O. Okay, we need 6 H2O. So this will become 3 O2 and, oh, I could just like, I'm sorry. We multiply this by 3, sorry, by 6. Because we have 6 H2O in the equation. Then delta H is negative 242 times 6. Okay. Right? H2O. Next is O2. Okay, 2O to O2, negative 249 kilojoules per mole. Okay, so 2O to O2. Okay, how many O2 we need? We need 7. Okay, 7. So that's like negative 249. Oh, we like reverse the reaction. Okay, O2 is at the right side. We put it on the left side. So positive 249 times 7. Okay. Okay. So H2O is check. O2 is check. C2H6 check. What we need now is CO2. CO2. Where's CO2? CO2 gas. This one. Okay, we're gonna use this one. 394. Carbon plus O2 going to CO2. Delta H is negative 349 times how many do we need? 4. Okay. 349 times 4. Okay. They're all gas. Okay. 1/2 oxygen. Okay. Tally check. Okay. 6 times 1/2 is 3. Right? 6 times 1/2 is 3. 4 times 1/2 is 2. 2. So 3 times O2 is 6. Then 2 times O2 is 4. So we have 10 oxygen plus 7 oxygen here. That's gonna be like 17 oxygen. 2O here, meaning... Oh, wait. Yeah, I'm sorry. Yeah, I'm so wrong. Alright. Let's take out carbon first. Okay. So carbon. Okay. There's 2 carbon here. Okay. 2 times 2. That's gonna be 4. That's 4 carbon. Then there's 4 carbon here. So that's balance. Right. H2O. C2H6. There's gonna be 2 C2H6. Then O2. Right. So 6 divided by 2 is 3. Then 4. I don't think we need this one. 4 divided by 2 is 2. Right? So 6 plus, so that's 3. 4, that's 8. 11. Wait, what? 4 times 2 is 11. Wait, what? Wait, is my oxygen not balanced? I think my oxygen is not balanced. How many oxygen do we need? 3 oxygen here. 4 oxygen here. We need 7 oxygen divided by 2 because that's O2. So 6 oxygen here plus 8. Oh, that's 14. That's balanced. Okay, we have 7 O2. I don't think we need this. Okay, so because, okay, this is 6 divided by, that's 3. 4. Oh, that's... Oh, we used the wrong one. Oh, we used the wrong one. Oh, we used the wrong one of carbon dioxide. Wait, okay. This should be used. Okay, I was looking at this one. Okay, so it's not 1/2. It's just 1. Okay, this is just 1. Okay. Okay, there we go. So we don't need this one. Right? Because basically, the combustion of carbon dioxide, the reaction of carbon dioxide will supply us with oxygen. So if we add the left side, that's gonna become 7O2. Okay? Then, H2, there's like 6 H2 here. 2 times 3 is 6 H2. So meaning, there's 6 H2 on the left, 6 H2 on the right. Okay, it's gonna cancel out. This is gonna cancel out. This is gonna cancel out. Okay, H2O, 6H2O, 4 carbon dioxide. Okay? So that's our main equation. We just need to, I'm not gonna include this, we're not gonna include this. We just need to add these three because this is not included. Okay? Okay, so I hope you guys are like knowing what should be added or not. Okay, the main goal is to have our equation, to have our original equation or get our original equation from the equation given to us or the reaction, the formations of the chemicals given to us. But yeah, we don't need the other equation. We don't need to use them all. We already got the equation from those. And this should give us around 900. If I remember correctly, negative 85 times 2. Oh, and that's like plus 249. That's very good. We didn't. Negative 242 times 6 plus negative 349 times 4. Okay, negative 85 times 2, negative 242 times 6, negative 349 times 4. Okay, negative 3018. Okay, that's perfectly fine. Kilojoules per mole. Okay, delta H. Okay. And this is now our Hess law. Okay. Okay, that's our heat generation from C2H6. Okay. So basically, that's Hess law. Hess law basically is like you can determine the heat of a reaction even without getting or knowing the heat of the whole reaction by just adding other reactions or mini reactions in order to get that big reactions. So, you know, if we like form a theoretical fuel that is not created yet, let's say 6200 H600, you know, theoretical fuel, you know, we could technically get the combustion. Technically, yeah, probably hard. You know, we can get the combustion if we have enough mini reactions coming from these ones, right? If we have, you know, if we have, but if we have. All right. So, well, I mean, guys, don't take me, don't, how do I say this? I don't want people saying in the comments, but you said we can make our own fuel. No, that's not what I said. But Hess law, yeah. Okay, if you want some definition, go get it in the anyways. Okay, let's just redox reaction. Okay. Fe2 plus Cr2O7 negative 2 going to Fe2O3 plus Cr3 plus. Okay. Balance the reaction in acid solution. Determine the value of the cell potential in voltage. Ooh, okay. Okay. We need to get it and we need to get this on, like, we need to get like a table for this one, right? Okay. So anyways, first, Fe2 plus going to Fe2O3. Right? So in this one, F is 2 plus. In this one, this is basically neutral, right? So 0 is equal to 3 times negative 2 for oxygen, F2Fe plus so that's negative 6 going to the other side, that's 6 to Fe. Fe is 3. So meaning that's 3 plus to 3, it releases an electron. So meaning is there should be an electron here. It releases an electron to the left side. Okay. What else? Okay, that's the oxidation. Because it becomes 2 plus to 3 plus, right? Then Cr2O7 negative 2 going to Cr3 plus. So this one is negative 2 is equal to 7 times negative 2 plus 2Cr plus, so that's negative 14 going to the opposite side. 14 minus 2, that's 12. 2Cr, Cr is equal to 6. So that's 6 plus 3 plus 2, that's like 3 electron here. Right? So meaning that's reduction, right? But because this is 3 electron, we multiply this by 3. Okay. Okay. So basically the equation is 3e negative Cr2 O7 negative 2 going to Cr3 plus. Then Fe 2 plus 3 times 3 going to Fe 2O3 0 plus E negative 3 because we multiply the equation by 3. If we add that, the electron will be cancelled. We will have now 3Fe2 plus Cr2O7 negative 2 Cr3 plus 2 plus 3Fe2O3. This should be like 2 and this should be like 6. Okay, this should be like 6 iron. Okay, 6. Okay, so to balance out the metals. Okay, it's not balanced yet. Okay, it's not balanced yet. So we have, in terms of charges, at the left side we have neutral charge. 2 plus negative 2. So 2 minus 2 is equal to 3 plus. Okay, 0 is not equal to 3, meaning the right side has like more charges than normal. Since we're in an acid solution, we're gonna have like 3 hydrogen plus on the left side plus 6 Fe2 plus Cr2O7 negative 2 going to 2Cr3 plus 3 Fe2O3. That way, the charges is equal, but because there's like 3 hydrogen on the left side, we could go with H2O, right? How many oxygen we have? We have 7 oxygen here, and we have like 6. No, F2O3, that's 9 oxygen. Wait, this is 3 positive. Oh, wait. Chotomate. Okay, let's not be hasty, okay? Okay, we're wrong. So we have 6 ions, 6 times 2. 6 times 2, right? Plus negative 2 is equal to 2 times 3. Okay, so that will become, so this is wrong. Okay, we need to check out the, we need to like use the coefficient. So that's 12 minus 2 is equal to 6. That's 10 is equal to 6. So we add hydrogen here, 4H plus, to make it 10, right? Plus 4, 10 is equal to 10, okay? So there's like 9 oxygen here, okay? And there's like 7 oxygen here, okay? So we should add 2H2O in here to balance the 4 hydrogen, and 2 oxygen, right? The hydrogen and the oxygen should also balance in the end. Okay, that's why I was like, maybe there's something wrong in my, that's why I was like hesitant to continue on my first charges, balance of charges. I was like, the oxygen should be balanced. I should not add oxygen on the right side because there's already 9 oxygen on the right side. Yeah, that's why I was hesitant. Okay, so this is now our balance equation. Okay, now I'm gonna use a little magic. Okay? I'm gonna use a little magic. You're not gonna see any of this. You're not gonna see any of that. We're gonna blur everything. Blur, 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 blur. Okay, and we're gonna get a table of data. Actually, ta-da, magic. I'm gonna take. So we have iron and chromium, right? Okay. So Cr2O7, this one, Cr2O7. Then we have iron. That's 2 plus 2, 3 plus. So we're gonna just opposite this. Okay. So notice, chromium is the reactant, so we're gonna use 1.33. Then iron is the product, or we're gonna use the reduction. So sorry, we're gonna use the oxidation of iron, but our given is reduction, right? This is reduction output reaction. So we're just gonna like negative it, 0.77. And since we multiplied iron 3 times, okay, the voltage or the EMF, okay, or the cell potential of the reaction should be, okay, the correct term is cell potential. Standard cell potential, because we don't have any change in concentration. 0.98 voltage negative. Okay, there we go. That's the standard cell potential. Okay, so basically the voltage is just like Hess law. Okay, it's just like Hess law, but you're talking about the electrons. Okay, just like Hess law, but you're talking about the electrons. Okay. Anyways, I hope you guys have learned something from this video, and yeah, this video is longer though. This video is longer, around like 40 minutes. But I hope you guys like it more. Comment below if you comment, in the comment section if you guys like it better or not. But the idea is I'm like sharing my knowledge. Although you see that I could also be wrong. I'm solving these questions with analyzation in mind. With like, what if you don't know, or you haven't like studied it, or what if you're gonna analyze the problem, you're just learning it bit by bit. Okay, so anyways, thank you so much for the time. Thank you so much for watching, and I hope you guys like the video. Goodbye. Bye bye. Bye bye. Bye bye.